Good morning, everyone, and welcome to Brandforsk and this result webinar. We will get a presentation of the results from the project Crowd Safety, Prototyping for the Future. And Håkan, Daniel, Denise, and Peter will present the project. And after the presentation, Håkan and Daniel will answer your questions. Now, Håkan and Daniel, would you like to say hi and introduce yourself a bit?
Yeah, good morning, everyone. My name is Håkan Francis, and I work as a senior lecturer at the Division of Fire Safety Engineering, Lund University. I've been partly project leader for this project in the end of it. Yeah.
Okay, Daniel.
My name is Daniel Nilsson, and I'm professor at the University of Canterbury in Christchurch, New Zealand, but I used to be at Lund University, which is why I was involved in this project.
Okay, thank you. Just a few words about Brandforsk. We have a vision, a fire-safe society built on knowledge. We develop and communicate knowledge, mainly research, to limit the negative consequences of fire in the society. We started in 1979, and since last year, we are a foundation. We have supporting organizations that fund everything that we do, and this makes us a collaboration between many parts of the society. And the funding so far this year is about 600,000 euro. And we spend our money, of course, on research, and we also do a lot of result communication like this webinar. And we also have a research school for practicing fire safety engineers in fire services. That makes them part-time PhD students besides their work in the fire service. And we have scholarships for students. These are our supporting organizations, and it's really thanks to them that we can do this. And as I said, the funding so far this year is about 600,000 euro. And the program for today, I'm beginning to feel ready with the introduction so that we can go to the presentation of the results. And after that, there will be time for questions and discussions.
Welcome to the presentation of the results from Brandforsk project, Crowd Safety, Prototyping for the Future. My name is Håkan Francis, and I have been the project leader for this project, at least in the final part of it. What we will be talking about here today is a new way of modeling pedestrian movement. And for this, we have had a goal showing how the science for pedestrian flow can keep up with the demographic change. The people that have been involved in this project are, apart from myself, Daniel Nilsson from Lund University originally, today at University of Canterbury in New Zealand. Dennis McGrath from University College Dublin in Ireland, and Pete Thompson from Autodesk. We also had a couple of reviewers, Karen Boyce from Ulster University, and Rita Fay from the NFPA in the USA. We also had a reference group providing with inputs from different parts of the industry and other organizations. Today, we will briefly cover the project aim and the state of the art. Then Pete will talk about the parametric analysis, and after that, Denise will go through all the experiments that have been done in the project. And finally, I will wrap up and introduce the roadmap suggesting the path for the future research in the area. But first, Daniel will start with talking about the project aim.
So I'll go through a quick review of the background behind the project, why we wanted to do this study, and also what the project looks like initially. And then I'll talk a bit more about work package 1. So next slide, Pete. So why did we want to do this research? Well, the discussion started, I think, at a Human Behavior in Fire conference, where many of the developers or the data collectors who collected a lot of the original data that we're still using, they were criticizing the data, since they were claiming that due to demographic change, people are different now than when we collect the data. We might need to rethink what we're doing. And the thing that was proposed was to recollect the data again, but in our group, we were thinking that there must be a smarter way. So the problem basically when we started was that a lot of the guidance document that exists, they're from the mid 20th century. A lot of the data is quite old. We're looking at data from the 60s, 70s, and 80s, and a lot of data from the Soviet Union and also from the US. And we know, for example, from the US that obesity wasn't a big problem in the 60s and 70s. It is today. So people have changed, but we're still using the same data. And we're also using data on a very aggregate, a high level. So rather than actually understanding how movement works, the way we've gone about it is to look at a certain evacuation of an arena, for example. We collect all the data we can, we plug the data into the model, and we get something out. Now, if demographics change, we're still stuck with the old data. So we wanted to rethink this and see if we could do it in a different way. So next slide, Pete. So what we set out as the project aims was, first of all, we wanted to see what the state of the art is. So what's the frontier of pedestrian movement or individual movement in crowds? We then wanted to identify the parameters that influence people's movement inside a crowd. So we want to look at anything from biomechanical factors that has to do with your gait, physiological factors, and we're going to go through a couple of those later on. But we realized that it's not just about collecting data, it's actually about understanding how people move in crowds. We also wanted to explore new ways of collecting data, so not just doing at a sort of a meta level and tabulating the flows and measuring the flows, but actually looking at doing new types of experiments that could help us understand how people move in crowds. We're going to go through that a bit later, but looking at, for example, the step length, depending on the density in a crowd, was something that we were thinking that would be really interesting to know something about. And then this has developed in the project. So we wanted to develop some type of prototype experiment. And then one part of this empirical data collection is also that we don't want to stop at just collecting data. We also want to implement it in some type of model. And you will hear from Pete later on how we've tried to develop or how we've tried to improve models. We've developed one model, and we've also implemented in a computer model to see how our new concepts could work. And the final thing we wanted to achieve was to develop a roadmap, since we realized that even if this is a good project, we will not solve all the problems. This is just scratching the surface, since we're rethinking how pedestrian movement should be studied, pedestrian movement in crowds. So we wanted to develop a roadmap so that from this project, we can continue and do more research, and not just us, but others as well. Since if we're going to collect data about pedestrian movement, it's not the task that 4 researchers or 5 researchers can solve. This requires the whole research community to do work together. So that was why we wanted the roadmap. Next slide, Pete. Now this is the setup of the project, at least as it was described in the application. So we had different work packages. Work package 1 was state-of-the-art review, see what has been done. And this was the starting point for the whole project. We then have a work package 2 called parametric analysis, and then a work package 3 called experimentation, where we developed experiments and also did a lot of the data collection. And then work package 4, which is the roadmap for future. And then we had a work package called project management, just to administer everything. And then we had different tasks under each, or different activities under each of these work packages. So next slide, Pete. Now, in reality, since it is an iterative process, they didn't follow each other in a chronological order. It looked more like this when we actually did the project. So work package 1 was a state-of-the-art review. We did that early on. Then we did a bit of parametric analysis, and also experimentation. But the experimentation fed into the parametric analysis, and Pete will tell you a bit more about the parametric analysis, but this was basically the first model of individual movement in a crowd. But the parametric analysis also gave us ideas of what types of experiments we should do. So it's an iterative process, as you see here. And then the final thing was the roadmap. So next slide, Pete. So we're going to go through the different work packages, and we'll start with work package 1, which was a state-of-the-art review. Next slide, please, Pete. And the state-of-the-art review, most of that work was done by a student, Andreas Hansen, who did like a literature review, but it's called a scoping study. So rather than doing the traditional literature review, which doesn't have a lot of, well, there is not a strict methodology for a literature review, but for Andreas Hansen's work, he used a very strict methodology to identify articles in which individual movement in crowds was studied. And the process was according to what you see on the screen. So the first step was to identify the research question. And the research question was quite important. And he worked a lot, Andreas worked a lot on refining the research question, since that guided his search in the literature. So that was the first step. The next step was to identify relevant studies. And what Andreas did was that he had a couple of different search terms, and these search terms were combined in different ways, in 4 different ways, to search for papers, scientific publications in a number of databases. Now, for the 35 papers that he read in full, he had a data extraction sheet. So he sort of had it's like a list of questions or a list of things that you should collect when reading the different papers, and this is called charting of the data. So he extracted data in a very systematic way from these 35 papers, and then the final step was to collect, summarize, and report the results. It's a very ambitious way of doing a literature review, basically. Could you move to the next slide, Pete? Now, what did Andreas come up with? Well, the whole aim of this was to study which factors that determine your movement inside a crowd. And from reading all of these papers, or 35 papers, he did this mind map, which is sort of that crowd movement or individual movement in crowds has been shown to be influenced by different types of factors. So you have the psychosocial factors. Here you have things like emotional states, if it's an emergency or non-emergency, the type of clothing, culture, gender, and so on. So those were factors that he labeled psychosocial. There were environmental factors, like the type of surface they were walking on, if it was stairs, if there was a stair gradient. And these were all aspects that were studied in at least one of the 35 papers. He also identified biomechanical factors and physiological factors like age and body mass index and so on. So this is basically the outcome, or one of the outcomes of Andreas's work, that he identified these parameters that influence how we move in crowds.
Thanks, Daniel. So the parametric analysis was informed by the deep literature review and a very rough early model that we'd come into the project with. And from the list of things which Andreas identified, we started specifically looking at things like the step length, the height of people, things directly related to demographics of people, and then looking at breaking down the motion of people in congested space to, first of all, the physical space taken up by their body, and then what we termed the contact buffer between potential points of contact of one person walking behind another. If you like a pedestrian form of traffic analysis, where traffic analysis does include things like response times, etc., etc. So we knew that things like response times were also related to demographics as well. So we were breaking it down into the physical space and the open space between potential points of contact. What you see on the diagram is, well, towards the top, interperson distance, which is just the point-to-point spacing between people. Down below, at the very bottom, step length is defined as the distance between what they call heel strikes on the ground. So the distance between, for example, the left heel touching the ground and then further forward in the step cycle until the right heel touches the ground. And what we term the step extent is really the distance between the back of the heel and the front of the toe at any point in time during that step cycle. So if you add up the step length and the foot length, that's always going to be more than what we term the step extent. So the step extent varies during the course of the step cycle. It's always going to be slightly less than if you add on the full step length along the ground and the foot length, just because of the way that the pedestrian cycle's tracked and measured. And the contact buffer obviously also changes and is a representation of personal space. One of the interesting cross-reference points that we found in the literature review was there were a number of studies breaking down the step length of people and the changes of the step length of the walking speed. So what I've done is plotted on the chart here the fit curves that people have put to the trend in step length of the walking speed, i.e. the fact that it reduces, step length reduces with lower walking speeds, but I only plotted them for the range of data which they were collected. A number of papers have published across straight lines for the entire duration, but actually when you dive deep into their background data, they've only got a limited data set. So where a lot of people have linear relationships, they tend to be in the sort of higher half of those speed curves. The more detailed analysis tend to use a curved representation, and that curve is represented by a power fit. So what you see on the left of that equation, S over H, is actually just step length normalized for height. So what they would do is they'd take the step length, divide by the height of that person, and then remultiply back to an average height of 1.72. So it's essentially normalized step length, and that's equal to a constant multiplied by the speed to a power. And that relationship was an interesting one to explore, because we could think about starting to use that in the form of our equations. The other aspect of looking at the step is the step cycle. So what you see in the red trace there is what we termed that step extent, the distance between the back heel and the front toe, measured as a total amount related to the long measurement of the let's call the full step extent, which is the step length plus the foot length, and the actual instantaneous step extent is a fraction of that, varying between 30% when both feet are in line at the shortest part of the step cycle, up to about 90% when it's near the point of contact, and fully extended step extent. And that's an important point to note as well, we'll refer to later. And the other part, looking at the comparison with traffic analysis, is that there's a basic standing still spacing between people, but also that contact buffer increases with increasing speed as well. So there's a comparison with the traffic analysis in terms of response time. So when you look at age-related response time goes up, and during the course of those experimentations, it goes up roughly linearly. And again, that's another aspect which we use to implement with regards to looking at the contact distance between people. And that buffer is really just looking at the boundary space between the physical extents of the person during the walking cycle. So this was the early version of our attempt at modeling step extent and contact buffer. The 5/9 power for that curve fit of the relating step length to speed. That came from an early fit on some tests by Tanawong, and Bobic. And the contact buffer made an early estimate that it would be a basic distance plus a response time. And we did some very early tests with that. I'm not going to go through the full representation of every stage of the modeling, just a general description of the principles and then the final form at the end. So, and by adding the step extent and contact buffer modeling, we can then derive the interperson distance. From the interperson distance, we can get the crowd density just by 1 over the interperson distance later. And that's how we back project everything back to the general flow parameters. So this initial parametric stage showed us that the relationship that we derived from adding those step extent and contact buffer together with these early approximations gave us a relationship showing that the interperson distance with the approximations that we chose did reduce with walking speed. The red dots that you see scattered across that plot in the right-hand side are from the raw data sets collected by a single file analysis by Chow and other researchers in 2016, where they plotted these red dots represent a cohort of young people walking around a loop cycle. And we measured the single file analysis for most of this project just because it would reduce the number of variable parameters on the way through. So in this early stage of the analysis, we had some fixed demographic parameters which we could use. For example, the individual height. We knew that the unimpeded step length was 0.414 as a fraction of the individual height as a statistical average across the population. So we could derive step length from height. We had the foot length, we had the unimpeded walking speeds, and then from that we get the variable parameters that change with time or speed: step length, walking speed, interperson distance, step extent, and contact buffer. And those are the things which come out of the applying the equations. And that early stage informed the experimentation, and I'm going to hand over to Denise at this point to talk about the experiments.
Thank you, Pete. Yeah, I guess you can go on to the next slide.
Here we go.
Okay, so our experimental goals then were to see if and how we can measure these sort of more granular parameters such as contact buffer and step extent in using different technologies and in different contexts. So our main interests were gate speed, interperson distance, contact buffer, and step extent. We wanted to understand the relationships between these variables, and we wanted to derive values that could then be inputted into our model. Next slide, please. So when I say different contexts, then what I mean is that we sort of leverage the resources and expertise available at both Lund and Dublin to undertake experiments to look at these variables. So on the left, we have some pictures there of the experiments that were undertaken by two students, Gabriel and Jesper, in Lund University. And so these students worked primarily on the experimentation work package. So you can see there that they were looking at trying to measure step length and contact buffer in varying densities. They used video analysis, and they had a large space that they could walk around. The experimental setup is up there on the top left. So they had two cameras and one both sides of the walkway and one overhead. They also used an eye tracker as well, a Tobii Pro Lab eye tracker, looking to see what information is useful to derive from that in the various contexts when there's low density, when there's high density. Then the students came over to Dublin in December, this time last year actually. And in Dublin, we have a smaller space, but we have equipment for 3D motion analysis. So this is sort of, quite a high resolution, highly accurate motion capture system that we would traditionally would have used just on, one person doing, various either sporting movements or walking, that kind of thing. But here we actually used it for, a multiple people, so single file flow of 4 people in a row. And we recruited 4 people 4 times, so we had 16 subjects altogether in this experiment. And we placed these active markers on their shoulders and on their shoes so that we could track them as they walked through the field of view of the 3 cameras that were set up. And you can see the experimental setup up here. So what we were trying to do here is we're trying to, okay, let's see what we can find. As I said, we hadn't done this kind of experiment before in terms of a number of people walking at the same time wearing markers through a capture volume. So we hoped again to get very accurate data on the contact distance and the step extent. Okay, next slide, please, Pete. So we undertook, a similar analysis. They weren't the same people, obviously, but they weren't the same participants. They were the same experimenters. But so we looked at ways to visualize the data that would be meaningful. So this is one example of looking at stride lengths in 2 people. So what you see there in one diagonal line is one person, and then the person behind them is the other diagonal line, and they're shown from both technologies, so the video capture and the 3D motion capture. So you can see that they're, it's a very similar patterning, and it's just the red and the blue are the left and right heels of the person in front and the person behind. So you can see there the times at which they get quite close to each other. Just to note that the people that are represented on the video graph on the left-hand side are about 10 centimeters taller than those on the right-hand side. So you can see then that there would be a difference in stride length there in relation to their height, and the walking speed isn't very different between those 2 representations there. Okay, next slide, please. Again, similarly, we're just representing here the contact buffer. So the distance between the foremost toe on one person against the lateralmost heel on the next person in front. And so we can see, again, it's well represented here. You can see how close that contact distance can come and using both technologies. So both technologies are giving us nice data, but just go on to the next slide there, Pete. You can see this is just showing variation of contact distance, the left in the video and the motion capture on the right. So you can see that the trace is actually much smoother on the 3D motion capture. The granularity is much greater. And indeed, the time taken to produce both of these graphs were very, very different. So the students they used a software called Canovia, and for the video analysis, and it was extremely manual, extremely time consuming for them. Whereas the motion capture was quite easy to pull out and plot this graph. Okay, next. So just to kind of summarize then our experiments overall. So in Lund, they used a single file and a wider, slightly overtaking, a more densely populated condition. The data was useful that they produced, but again, it was time consuming. And in fact, Jesper is now continuing. The thesis has long gone in, but they're continuing to actually process this data at the moment. The eye tracking equipment, so the eye tracking, of course, one person at a time wears it. So what they did was they used it on a selection of shorter people and taller people. So I think it was 5 shorter and 7 taller people, and just looked at preliminary analysis of what people are actually looking at when they're walking. And what they found was overall, people are looking at route planning and the environment mostly, and the proportion of time spent looking at route planning and the environment increases with increased density. And then they also showed that taller people tend to look at the person second in front of them, and they tend to look at the heads, whereas shorter people look more at the person right in front, looking at the shoulder and back areas. So, they were interesting findings to come out of that, and it was certainly an easy technology to use. In terms of the data collection in Dublin, so we, you saw the laboratory set up there. We had, it's about a 12-meter walkway. We had 5 different gate speeds. We used our code of motion active markers, and we also attached an inertial sensor, so containing an accelerometer and a gyroscope to the lower back, just one accelerometer, with the view to estimate stride length, which that has been done before. It's not, it's an estimation. It's not completely accurate. So our findings from that, again, we're continuing to process this data at the moment. We had 2 other researchers working on this over here in Dublin. We included 2 different conditions in this experiment. So we had people walking in 5 different gate speeds in a steady state. So they were just told, okay, walk at this speed and don't overtake, and that was it. And then in the interrupted flow, we had a research assistant at the front that stopped kind of abruptly, unpredictably as they walked. So that was our interrupted flow. So we'll show you some plots there in a second, but generally speaking, interperson distance increased with speed. This increase was derived more from step extent than contact buffer. As you can imagine, there's a much greater distance covered by step extent. And there were some differences between the steady state and the interrupted walking. In terms of the inertial sensor data, that post-processing is still ongoing. Okay, so this sort of sums up the first analysis of the data. So what we wanted to show was that our assumption that interperson distance is made up of step extent and contact buffer. We wanted to demonstrate that empirically. So we measured interperson distance from shoulder to shoulder. That's what we called interperson distance in this experiment. The reason we did that, normally you look at it from the center of the hip, but because we're talking about a line of sight technology, if you have a marker on the hip and your hand is going over and back, it's going to occlude the marker, so the software isn't going to pick it up. So that's why we had it on the shoulder, with the limitation that the shoulder, moves a little bit during walking, although we had it on a bony prominence. So what we can see here is that there's a gradient with increasing distance with speed, with walking speed. And that is the case for both step extent and the contact buffer. And this is in the steady state walking. Pete, next slide, please. This is in our interrupted test. You can see the data has more of a scatter in the interrupted test, as you would imagine. And again, what this is showing is that our assumption that shoulder to shoulder distance is made up of contact buffer and step extent is in fact, true. As when we're talking about the mean shoulder to shoulder distance. Obviously during the gait cycle, it goes over and back. So we kept it at a stage where we could get a sort of an average shoulder to shoulder distance.
So as I said, I'm not going to go through every one of the different developed versions that we went through during the project. I'm just going to cover where we ended up at, given the information informed from the study and all the biomechanical and video and motion capture testing and feeding back through that process. So we end up with slightly more complex form of the equation, but essentially still breaking down into these components of step extent and contact buffer. One of the outcomes from the experiments was that during the course of the step cycle, the point at which we have the smallest contact distance is somewhere near the maximum step extent. So where the furthest distance between the heel at the back and the toe in front is usually somewhere near the smallest contact distance. So that's generally relates to the roughly constant interperson distance. So if you can predict those two, then you can predict the general interperson distance and speed of the group with similar demographics. So this form of the curve, remember we had the power curve for the step extent. So we've got here, in order that we can relate it to demographics, we've got the unimpeded speed with the speed at any point in time as a fraction multiplied by the unimpeded step extent, with the same power relationship derived from Wang and Seefried. We add on the foot length, and then we just multiply that by a fixed factor A, if you like. Roughly, from the early video tests, we got around about 90% of the unimpeded step and the foot length was roughly approximate to the maximal step extent at lowest contact. And then once people have achieved above a basic minimum comfortable personal contact distance, then it's a relationship between speed and a very basic response time. And those relationships seem to hold true through our various tests. We wrote a spreadsheet to break that out. And then we were very keen to compare those results with other testing. And more recently, there have been some very specific tests on single file flow. We chose to compare against this test by Chow and others in China a couple of years ago, particularly because not only did it have a young student group, but they also had an elderly group over 60, over 65. And they did 3 sets of tests, one of which was the young student group, one of which was just the old group, and then others which was a 50-50 mix of the two groups together to see what the consequence of that was, around basically just a loop. They had different colored hats to use their tracking software and also represent the natural speeds of the different people. So from the Chow cohort, we had some average heights for the young and the old in the group. We had some average speeds for the young and the old. Obviously, the older's average speed was lower. We used the 92% factor for the step extent versus the unimpeded length and foot length derived from Tanawangsuan cycle. The foot length averages were taken from a paper we found on the shoe size, and the contact adaptation time is based on the basic response time for young people, and we added on tests which were done to look at the difference left in that an approximate sort of treadmill situation by elderly people and young people that were done before this project started. We had some treadmill tests where we had a mannequin in front, and we had young people on the cycle and elderly people there, and they left a larger gap. We reevaluated that as a difference between the two, and added on the elder response time. And then also the two groups had maximum single file densities as well. The elderly people left a larger gap even though they're comfortable standing still. So we fed all that data into our equation. First of all, looking at the step length, so looking at the individual components and comparing. So the red and the blue lines, our predicted step lengths using the relationships I just talked about, and the Chow cohort data. So the red curve is for the young on our predicted curves. The blue is for the elderly on our predicted curves. And the purple one is for Wang and their study of experimentation looking at a young cohort. So it gives a very encouraging agreement for that component of step extent. And then we took those formula and applied them to a spreadsheet to derive the full interperson distance at any given speed. And again, the red curve is for the young cohort, and the blue curve is for the elderly cohort. I know we've got the blue dots and the green dots on these charts. All the dots are from the Chow experiments 2 or 3 years ago. Red dots and red line are for young cohort, the red dots from the experiments. The red line is from our spreadsheet application of the formula. The blue line is for, if you like, a homogeneous 100% elderly from our spreadsheet formula. And the dots here, the blue dots, are for the old cohort only, and the green dots are for the 50-50 mix of the young and the old. And it's interesting to note that in their experiments, when you had the 50-50 mix of the young and the old, the performance of the elderly dominated the flow. And when you think about it, that makes sense, especially in this single file scenario. They also stopped taking data for the elderly in the later tests as the elderly got tired, which is why there's no blue dots further down. But again, an encouraging relationship based on our derivation of these individual components. We gained a deeper understanding of the crowd movement parameters from all this parametric analysis. The single file model prototype used individual characteristics and to at least give what appears to be reasonable trends and some good degrees of magnitude on the performance of the modeling. The new experimental approaches gave us quantified metrics that we could use. The modeling approach is promising for mixed populations particularly, and also the technical approaches were investigated, and the experimental investigations which Denise showed also illustrated some of the challenges and opportunities ahead.
In order to put all the results from the experiments and modeling into a context, we have developed a roadmap pointing out the research direction for the future. It points out what should be done on a short, medium, and long term, with a vision in the horizon. We have 3 important areas for research. We have primary parameters of movement related to identifying and collecting data. We have another research area related to experiments and the data collection techniques. And finally, the last area of research is related to modeling and modeling implementations. They all have a vision here to the right, and they are structured on a time scale for doing the research. As an example, we can look at the research area, experimental methods and data collection. And on the short term, we should explore and use known techniques like video analysis that already exist today. On the next step is to develop techniques currently not used in our field today, but they are existing in other areas. And finally, to explore techniques that are not very well established today, but might be relevant in the future. And this research has a vision, in summary, to identify techniques and to validate these techniques to be used for data collection. So, to summarize what the project has resulted in, we have had 4 students being part of the work, resulting in 3 different theses. We had 2 conference papers and 3 journal papers, of which one is already submitted to Fire Materials, and the other 2 are still being written right now. And the future research is to continue to analyze the data and perform other experiments to refine the models that are being developed using these techniques that we have been talking about here today. So in summary, these are the main outcomes of the project. We have been working with movement parameters which have been identified. We have provided a new analytical model for pedestrian movement. We have done quite a number of experiments validating and providing input to this analytical model, and we have also done some batch simulation flows to validate these models. And we have developed this roadmap and provided a final report from this project, which is available at brand.lth.se. Thank you.
Thank you. And I will read the first question here. It's regarding your model equation for interperson distance. How does it depend on how many people are involved in the dynamics? I can easily imagine that the situation is very different if one compares low density with high density pedestrian flows.
Of course, it differs depending on the crowdedness of the situation. What the models are doing is basically to derive the movement characteristic, the movement speed for individuals, and that will be dependent on the crowd density. So if the crowd density is high, that will result in shorter step lengths, which in turn will lead to a lower velocity. So of course it matters whether or not the situation is low density or high density. That is true.
Yeah, is that a dynamic thing or a behavioral thing?
I would say at the moment it is a dynamic thing. It's related to movement, but there might also be other factors that could affect the walking speed, which we haven't looked into so much yet. But there are a lot of different parameters that will be involved and be depending. Which the movement speed will depend on. What is important to recognize at this moment is that we are actually taking only the first initial steps in this new way of looking at how people actually move, taking a step away from this global perspective, looking at only the density relationship with walking speed, but in fact looking at how each individual actually moves depending on some key basic parameters. So there are probably a lot of other factors that will contribute to the movement pattern and the movement speed, which we haven't looked into so much yet.
Could I add to this as well? Since
yeah, please.
What is surprising though is how well it fits. So even when you have sometimes in pedestrian movement, you talk about the laminar flow, you talk about the stop and go when it becomes more crowded, and then sometimes you mention the turbulent when bodies are touching. We're not going into the turbulent regime since we're not at those densities. But what is a bit surprising is that the same model gives relatively good results for the laminar flow as well as the stop and go waves, which is a bit surprising since stop and go, you have sort of the staggered movement. So you move, you stop, you move, you stop. It's not smooth, but still a lot of the reduction of movement speed can be derived back to step length as well as the space you leave in front to not collide with people. So even though we haven't identified all the parameters for all the different densities, I think we're on to 2 parameters that are very, very important. And that's sort of, this was a very early well, it was a pilot project. So that was sort of what we set out to achieve.
Right, thank you. And we have another question here. What can tell single file pedestrian flow modeling and experiments on the general motion of human crowds?
It's a good question, and it's also, I mean, part of the reason why we are studying single file movement is that if you're looking at a crowd, it becomes very, very difficult to see people, since you have persons all around you and you can't really characterize the step length. So this place to start is single file movement. Now, the next step, and that's also part of this experiment, is to look at how can we use inertial sensors. Are inertial sensors accurate or not? Since if you use inertial sensors rather than optical sensors, then you don't have to necessarily see the person. So part of this project was testing the methodology, and the place to start was single file movement. We can still learn a lot from single file movement, but in the next couple of steps, we have to move into accurate measurement techniques for crowd movement, where people are obscured by other people around them. So it's an interesting question, and it's, well, yes, there are differences. We can learn quite a bit, but we need to take the move to measurements in actual crowds, where you just not only have a person in front of you, but sort of sideways in front of you and sideways behind you. But that becomes a measurement problem. It's quite hard to see how people move.
I can add also to this answer in relationship to the roadmap. The roadmap is showing research that should be done in different fields of research. So that is why it's so important to also include development on the measuring techniques at the same time as you look at the different variables that should be included in defining how people move, because you need to develop these measurement techniques at the same time, because otherwise you may end up with techniques that aren't possible to use. For example, if you cannot see people, then optical methods aren't that useful.
Right. Thank you. We also have a question here about wheelchairs. Have you been thinking about how to incorporate them into a model like this, and how can they affect this?
Yeah, I would say that wheelchairs aren't that different from an other person, other than there are some factors that need to be described a little bit differently. But basically, a wheelchair user will probably have to adjust his or her sort of movement speed in the same way, looking at sort of the possibility of not contacting the person in front. So I wouldn't say that's a very big difference, but of course there is another parameter apart from the step length that should be included in the model. But that is something for the sort of next version of the model to look into.
Yes, and we all have another question on the same subject. Will the roadmap include equipment on people with disabilities in method and model calculations?
We do have more on a sort of general level, but one of the things we want to look at later down the track is individual characteristics. So we've talked about things like BMI. If you have a limp, for example, how does that influence how people keep a distance to you? We haven't been as specific as saying canes or wheelchairs or so on, but it's sort of in that general domain of looking at individual characteristics, not just young, healthy adults or only elderly or a mix between the two, but actually looking at if someone is walking with a cane, for example, how do people move in relation to that person? That's also why we trialed the eye track. We just used it for the first time just to see what people looked at in crowds. Got some interesting results, what you look at high versus low densities. The next step would then be to put eye track on people walking behind someone with a cane, for example. What do they look at? How do they overtake that person? And those types of questions. But that's further down the line, I think. For now, we have to grow our model find all the factors, and try to refine it.
And as a first step, we did this scoping study to identify what we then said was the 22 sort of key parameters that were important. But of course, there could be other parameters that we aren't aware of really yet, or they aren't at least defined in the report. But most likely there are some other factors that we have missed that should be included in future studies for if you sort of look at the roadmap structure, the first row.
Yeah, I found it very interesting about the eye track and how people relate to people ahead of them, if they are taller or shorter, and how they. I think it's very good. One thing I read with great interest in the report was the study by Andreas Hansen and the method he used. Was that developed in the project, or was it a method that you picked up somewhere?
That method exists. It was the first time, at least I used it with one of my students. But it is usually in the past you can be a bit sloppy when you do literature reviews. You sort of define your search term, you search in a couple of databases, and you might describe it. But this scoping review or scoping study was a very systematic way. And you could see from the slides, he started out with 5,000 papers, and then reading titles, going down, reading abstracts, and then in the end, he found hopefully the 35 papers that were most relevant. So it was not developed in the study. It is something I suggest you try out if you want to do a literature review. It's time consuming, but it does get you on the right track. That's my sense of it anyway.
Yes, very good. And of course you can read about it in your report. I have a question for you. Now that you know this, if you with your knowledge today, if you compare what you're aiming for with this work, and you compare that with the models used today, the older ones, with a macro perspective, what are you feeling about the accuracy in the old models, and do you want to give some specific heads up on things to be careful with, where you can see that probably the uncertainty is quite large in the old models?
Well, I wouldn't say that the models that exist today are poor or inaccurate. Of course, there are large uncertainties involved when we're talking about human behavior and pedestrian movement and so on. You could see that on the slides as well. There are some slides from experiments that showed a significant uncertainty in the results. But I mean, the point here is to have a new way of looking at how people move, not necessarily to say that this is because the old models aren't good enough, but it is a way to better adapt to changes that we can see in the society today, that people change, the demographic change. So in order to keep up with these changes, this way of modeling is a little bit easier to adapt to these changes that we can observe, compared to do all experiments all over again, looking at the crowd flows in various situations with new groups that should be in the experiments, but instead looking at how certain factors related to biomechanical properties, for example, how they will affect how people move, will make it easier to adjust for the changes that we can see in the society.
And as an example, as Håkan mentions here, a lot of the models that exist are usually based on some form of the fundamental diagram. So that's the correlation between speed and density. Now, the problem with the fundamental diagram is that it's not really fundamental. It is fundamental it is for a specific population. So if you go and collect data in Japan, then you get different results than if you go and collect it in the US. Now, part of the reason for that is that in Japan, the average height is people are shorter than in the US. Hence, they take shorter steps. Hence, they can keep closer together. So you get a different fundamental diagram. They might be moving more effectively at high densities, for example, if you measure the densities as persons per square meter. Now, with this approach that we've developed, rather than just recollecting as people become bigger or larger or more unfit, we can get the characteristics of the people, plug it into the model, and grow the fundamental diagram rather than just recollecting it all the time. So it's a new way of thinking about movement rather than just collecting data, putting the data in the models and getting whatever we put in as output. We're now thinking about how can we use reaction time, how can we use step length, how can we use a limp, if someone has a limp, put that in the model and get realistic results. Since those types of things like reaction time, we can either measure or we can derive, we can get it from traffic, we can get reaction times, for example. So it becomes more flexible.
Yes. Mentioning reaction times, your test persons were quite young, and they had, and you show that reaction time is really important for the interperson distance. How large is the variation? Do you have any knowledge about that when people get older, or?
Yeah, I mean the reaction time is longer for elderly people. Obviously, that has been shown in the literature, but also within the same age group, I would expect that there are some variation. And looking at the data from traffic, you could see that the variation could be quite significant. So what I think we need to look into also in the future is this variation for all factors that are involved, actually, because there are large variation within populations, within well, for example, in the same age group. So we cannot just say that a person age 19 is walking with 1.5 meter per second, because that is not true, because the variation is so large for this age group. So that is something that we need to look into more into the future that has been into the past. So that will probably affect the way we design evacuation routes. How should these uncertainties and this variation, how should that be included in the design assessment in the future? Because I think we have sort of not neglected perhaps, but focused a little bit too much on average values and not seeing the variation so much.
Right. Very good. I think in the audience today we have a lot of practitioners. Do you think what can be picked up from this work so far in your report? What is there anything that can be used today by designers?
I wouldn't say that directly, because this is a pilot study, and we have actually basically shown that the concept worked. We have done some computer simulation using this equation that was not part of the presentation, but there was a master thesis work showing that there was some great the results showed that there was a quite good agreement between experiments and the modeling results. So I mean, in the near future, I would expect that we can see submodels that are in computer simulation models that will appear. Maybe not today and not tomorrow, but not very far into the future. So that is probably the closest that you get to the practical situation.
Okay, thank you. Now we have no more questions from the audience. And do you want to add something, Daniel or Håkan?
Yeah, I could add to the last question about the importance of the study. Even if modeling pedestrian movement is not the most sort of practical applied that you can use today directly from the project. But I would say that there are important factors that are introduced in the project, for example, from the scoping review, which shows what are important factors to consider when looking at pedestrian movement. And that is something that could be sort of relevant already today, actually, in design, to see what characteristics should be considered, at least, maybe not in a quantitative way, but at least qualitative. If you look at different population groups, that is something that could easily be picked up.
Oh, very good.
I would also like to add, we published a roadmap, and it's a relatively ambitious roadmap, and nothing that the four of us could ever solve in a lifetime, I think. So just encouraging other researchers who may see this and are interested to connect with us, and we'll chunk off different bits and pieces, and we'll do a bit of research, since it's not a 1-year project, it's not a 5-year project, it's a long project for a lot of researchers. But what I feel is that we're onto something, and we need the researchers to focus on this, not just us.
Excellent. Well, thank you. I think we're gonna just wrap it up here. Thank you for the good questions, and thank you, Håkan and Daniel. If you want to attend more Brandforsk webinars, you can find them at our website or by following us on LinkedIn. You can also register to our newsletter. You can find that at the bottom of our website. We also have a YouTube channel where you can find earlier webinars and recorded seminars. And if you don't know Swedish, I think you can figure it out. We are working on an English web page as well, but it's not up and running yet. And I also like to thank Francis Severinius and Matthias Hammarin, my colleagues that have been producing this webinar. Thank you, Francis and Matthias. Work well done. And I hope to see you soon again. We have another webinar tomorrow that will be in Swedish, and it's about CIP, Civil Insatsperson. You can see that at 8:30 on the same channel. And thank you all for listening and attending. Bye-bye.